Well, fans of flying objects will be very pleased with our next guest, as you may have been pleased with the previous guest. My God, if you hadn't had enough of flying vehicles at this camp, we have finally got the talk for you. Katha is here, and I know this because she's standing to my left, and she's going to take us on a journey, and so let's welcome her with a warm round of applause.
So welcome everyone, and thank you very much. So this talk will be about modeling and control of unmanned aerial vehicles. So it's about autonomous flight of aerial vehicles, so anything like a helicopter, quadrocopter, whatever. If you actually want to buy something like that and fly around with it yourself, you should talk to those guys behind the tent. This one will be about math and not setting it up. So that's a autonomous flying object. But, well, it might not be controllable. Just looks funny, that's all. So it's broken, of course it's broken. So when we talk about aerial vehicles, there are of course different different kinds you can set up. So just one example we did at our research group, that's perfect. So that's life. So what you should be able to see is a helicopter hovering in a position and then flying a circle. And so that's what we want to achieve today. The big advantage of helicopters is that they can start vertically, so lift up, that they can hover at a certain position, which is pretty important for certain tasks, and then fly any direction they want to. And pretty good pilots can, there it is, fly as well, just inverse. Thank you. So just doing a circle kind of thing. So there will be a picture of that helicopter later on. It's a small-scale helicopter. And coming back to the slides. No. Sorry, I'm not a Mac user. So there are different setups of your helicopter or your rotary ring copter you could choose. So first approach would be just to choose one rotor, but that wouldn't work because you would generate a thrust that would result in the whole thing just turning like those little seedlings of trees you see not here but everywhere else. So the first approach is to add a second rotor at the back, so a tail rotor. The laser pointer is not visible. And so the helicopter stays stable. But there are different approaches as well. You can just add a second rotor below this rotor, a second rotor at the back, or a second rotor next to this rotor, and they are always turning in the opposite direction, as well as, that's a pretty cool setup, you just use two that interlap, like the whisk of an electric mixer, and the third setup would be a tricopter. We have two in front and a tilted version in the back that counteracts as well the generated thrust of the rotors in the front. The fourth setup, it's pretty famous about for micro-scaled copters. Those are flying in the back here. Would be quadrocopter, so set up like that, where you align them just in kind of cross, but you could also align them in a cross like that, or you could choose like 8 rotors or 12 or whatever. The big advantage of the high number of rotors is that if one fails, you have enough left to, well, at least land safely. So the video we just saw, it's a Bergen industrial twin we worked with. That's a small-scale helicopter. So those that are flying around here, something like that, or the quadrocopters, They are called microscale helicopters, so they're pretty light. They have different properties compared to this one, which is basically a small version of a real helicopter, because it already has a Bell-Hiller stabilizer on top of here, and pretty neat properties we'll discuss later on. So, modeling these things. Well, you have some things you have to set up first. First of all, the body frame of the helicopter, if it's moving around, it has its own frame. Sorry. It's moving around in its own frame. So, so that's the body frame in X direction, Y direction, and that direction. And so I have roll, pitch, and draw motion. And of course, velocities, translational velocities, and angular velocities in these directions. The helicopter is heavy, so it has some gravity forces on it. It has some drag forces indicated by VD, as well as some forces generated by the stabilizers. Sorry. As well as the generated. It's not holding. Can you hear me? Yes. So as well as you generate a thrust with the main rotor, tail rotor, and it talks with your rotors. So, sorry. So it doesn't play a role how many of these rotors you have. You always generate a thrust. So if you have 3 rotors, you of course generate it with for all of these 3. So the important part about the body frame now is that it's a moving frame. So you accelerate it, you rotate it, and this means you can't apply standard laws like Newton's law. So what you do is you have a ground fixed frame, like where we are, and you have a body fixed frame of the helicopter. Sorry. And you have to rotate your ground fixed frame, which is inertial, to your body fixed frame, which isn't inertial. And you usually do that by a rotational matrix where you project, indicated by the dot product, your ground fixed frame, but all your GPS coordinates and everything, to the helicopter so that it knows where it's orientating. And standard approach would be just to use Euler angles for that. It's pretty obvious and straightforward approach. So the top line is the ground fixed frame, and the bottom line is the body fixed frame. So, and you just pitch, you roll by minus half of pi, you pitch by pi, half of pi, and you draw by pi, and then you turn your helicopter. But that sequence is of course not unique. You can just rotate first, pitch first, yaw first, and then do all the other stuff. So you just choose one sequence out of the 12 possible ones. That's not a problem. But Euler angles provide a really big problems because they can exhibit singularities. For example, choosing half of pi for jaw results in singularities, and if you're doing some numerical analysis, that just blows up everything. So you're inverting matrices that are singular, and it's not nice. So you could just say, okay, I choose a different sequence out of the 12, but that's not possible. Any of these 12 sequences exhibit singularities. So we do another thing. That is, we choose quaternions. Quaternions are pretty nice, but they're not as nice to imagine as like Euler angles where you just turn by pi. They were introduced by Hamilton, and they are an extension to real numbers, just like complex numbers are an extension to real numbers. And so you have basis vectors in Hamiltonian space of 1, I, j, and k. And they have, of course, some neat properties, like they are bilinear, distributive, and most important of all, they are non-commutative. That means you can just multiply them as you want, but you have to keep in mind that some extra rules apply. So the big advantage now is that you have 4 elements, and you only want to describe 3 positions in a 3-dimensional space. And what you do now is you obtain your rotational matrix. It looks a bit complicated. You don't have to keep in mind all these entries. And if there's some numerical issue which could appear if one of these quaternions is going towards 0, you can just choose maximum of solutions because, well, you have 4 quaternions for 3 positions, as well as the rotation matrix is an orthogonal matrix, so you have as well some redundancies in the entries of the matrix. So it's a pretty nice approach, solving every problem with the rotational matrix, but it doesn't look that nice. So we can come to rotor aerodynamics now. There are different approaches to describe rotor aerodynamics, so what's happening when the blade is turning. One would be momentum theory. It just regards air above here, which is basically moving at a velocity of 0, and the velocity of the air right below the blade, which is something. And then you can just compute differences and say, okay, I'm generating that and that thrust. But it does not take into account the speed of the rotor if this helicopter is pitching or something else. So another theory would be blade element theory. So we cut the blade at any length, so just a cut through the blade. And basically like finite element theory, you integrate over the length of the blade. And so here's the first difference between helicopters like this one and the nice tricopters out there and quadrocopters. They have propellers, and helicopters have rotors. So they have a cutout in the first part. So you have to integrate beginning here to the tip of the blade, and you don't find that with propellers. Furthermore, there are some nice effects happening at the tip of the blade. You have some vortex effects and tip loss effects, reducing your thrust. And if you integrate over the whole, I'm sorry, it's not working. If you're integrating over the whole circle, you get as well the generated torque at the considered rotor. So taking into account the number of your blades and the number of your rotors, you can just simply compute thrusts and torques. We'll see some formulas later because they always are not of interest. So you don't just want your helicopter to move like that, you want to move like that or like that, hopefully turning as well. So what you do, you can, sorry for the people in the back, there is something called collective and cyclic pitch enabled by the swash blade. So you can actually turn this thing, which enables the helicopter either to roll or to pitch forward by simply tilting the whole plane of the rotors. It's a bit unstable, you can't see it in the back. And furthermore, what happens with helicopter blades, they are pretty flexible. It's a pretty important thing for helicopters because that enables them to fly. So first of all, you have the roll and pitch motion enabled by this swash plate. And second of all, which is not possible with propellers because they are just fixed and pushed backwards. Those rotor blades, they start to flap when the helicopter is moving. So they look pretty loose, but when they rotate, you have aerodynamical forces as well as centrifugal forces, which on one hand push the blades on the outside as well as inside, so they really align in such a line so the helicopter can fly. But they also enable the helicopter to fly at all. So by generating this flapping motion, you have forces generated at each blade that generates the appropriate torques at the main and tail rotor. So they also generate some problems because some of you might heard about it. If I have a real scale helicopter, the approaching, or it's the case with any helicopter, the approaching blade is faster than the helicopter itself, and the retreating blade is slower than the helicopter. And for real helicopters, the approaching blade can also be faster than the speed of sound, so that's pretty fast, which results in a lot of unnice effects, like you have some like oscillations occurring, you have some shaking, whatever, which could result in the blades falling apart. Also, if the helicopter flies too fast, it can start to pitch to one side. It can start to pitch. Sorry, that's wrong. And because of these differences in the speed, the forward blade starts to move upwards because of the generated thrust, and the retreating blade starts to move downward, which can result in braking as well. So we overcome these effects by something like Bell-Hiller stabilizer. That's the whole thing, where you have I can't see it. So you have some things, connected that stabilize control inputs that you do yourself, as well as disturbances like wind. And you can have something like a flybar, so that's something like that on top. You can have it below as well, that overcomes disturbances by wind, for example, as well. You don't find Bell-Hiller stabilizers or with quadrocopters, but you always find them at least at small-scale helicopters and with large-scale helicopters. You can also do that in an electrical way with a gyroscope or Venturi sensors. So for any kind of copter, you wouldn't regard this stuff. So you would just write down a model, keeping in mind that, well, your center of mass is somewhere here, because you have your batteries, your tank, whatever, in the front, and then you have all the way to the tail rotor or your other rotors. So you have some lever arms that you have to account for in your model, as well as the heights of your rotors, and then you just put it all together in a simple model for your copter of any size. So you have your rotary ring dynamics, your tail rotor dynamics, the rigid body motion, as well as some additional forces like a drag. And so this would be a really simple model you could use either for a helicopter or for a tricopter quadrocopter. And you can also add all the stuff like the tail stabilizer, so something small like that, or Bell-Hiller stabilizer, the flybar, so you can make it arbitrarily complex. But, well, it's just a model, so add as complex as you want it and as good as you need it. So we could, at this point, start to model it now, start to control it now. So we have our three translational velocities in U, V, and W. We have angular velocities in P, Q, and R. And we have only inputs, that is generated thrust at main and tail rotors, so T's, as well as the cyclic and collective pitch angles, that is beta, and that's it. So you have a big problem because you have 4 control inputs, so cyclic and collective pitch, as well as generated thrust here and there, and you have 6 states, so you have an unactuated system. But it can be solved. Before we come to that, how we do that, to the control part, we have to define one last thing, that is the actual path we want to fly. So you want to hover, so you start, you hover, you fly around. So what you do now is you define your path as a cubic function where you say, okay, my starting velocity and final velocity is 0. It's nice if it's 0 at turning points because that makes it nicer mathematically. And we say, okay, if I have an intermediate point, this velocity shouldn't be faster than half of the sum of its neighboring points, so something pretty nice to follow. So with that defined, we can actually go into control theory. So I know at least one of you is from control theory. The rest might not be. So what's control theory about? So there are different approaches. The simplest one would be feed-forward control. So you have your controller, you have your model, your plant, your vehicle, whatever, and you just say, okay, I want to go there. You push it there and you hope it gets there. Well, it usually doesn't because you have some disturbances, some errors, some noises, some modeling errors, whatever. So what you do is you feed back either the position or some volume of your tank or whatever, and then just compute differences of where you want to go and where it actually is, and then you push it further. But that as well can get arbitrary complex, so just adding an observer of where your plant is, or for example, doing some state estimation like, okay, I don't know where it is because I can't measure it, so I'm expecting it to be somewhere, and then I'm doing something and hopes it's doing what I want it to do. Or some filters to filter out noise, errors, whatever. So with that in mind, and remembering that we have 6 states and only 4 control inputs, we already know that controlling a helicopter might be a pretty hard thing. So it's an underactuated, nonlinear, of course, multi-input, multi-output system. And for control guys here, it's a non-minimum phase system. So there are some unstable gyrodynamics. It's non-flat, which is a pity. So flat system means I have one state which can control everything, one which I can use so I can use one output as an input, but I can't reduce it to a ruled manifold. So manifold is a nice thing in control theory, because if you have a stable manifold and you can reduce stuff to it, well, it's stable, and everything on it is stable. So what we do now instead is, okay, we do a little trick. We split the system, and we say, I have 4 control inputs, and I now control 4 of the states with these 4 control inputs. First of all, we do a position control. That would be the first part. And then I control in a kind of inner loop 3 of the remaining states. And then I say, okay, I just assume the whole thing is stable, and then choose 2 of the stabilized thing as my control inputs. And that actually works. It's kind of a trick, and it's a nice thing that actually works out. So some math at that point. I hope I don't lose anyone. So what you do now is you use your rotational matrix, so just R is the rotational matrix, to do your position control. We define our position in that nice trajectory. By defining a new input, so we have some gain matrices where you do just some pole placement, so you move everything to the 0, no, to the left plane. I don't know, I was confused with that. So that you have nice poles and everything is stable. And so gain matrices is just done MATLAB Mathematica, whatever. Maxima is a free software, and that provides a reference for your position, and you can say, okay, I just use a certain gain to stabilize my position in one direction, and then I move on and say, okay, I control, for example, so that dynamics, that was that direction. And when we choose the appropriate equation, we just see, okay, the translational velocity had just thrust of the main rotor because, well, it's just moving up and down. Then we can stabilize it pretty simple by using feedback linearization, so we're just feeding back where we are. And thus, the main rotor thrust is now not an input anymore to my system, but a known parameter because, well, I know where I put it, where I set it to, where put the helicopter where I want it. So what we have left is the velocities in this direction as well as angular velocities in any direction. So what we do now is we use our three remaining inputs, that is thrust at the tail rotor as well as cyclic and collective pitch of the rotors, to stabilize our three angular velocities. And we do that as well with feedback linearization. So again, feeding just back where I am to put the helicopter where I want it to be. And it's possible because the system is of full relative degree. Another nice control topic. And then this enables asymptotic stable tracking of my curve I set. What we do then, we have a new input that we can define because, well, I know now how it's moving in these directions and how it's moving in that way. So I can just say I use these four inputs that were former inputs as a parameter as well as the angular velocities and stabilize that way velocities in these and these direction around these points. Sorry, that was too fast. And we do that by linearizing the system about the trajectory I gave. So a general approach, that's just a Taylor series. So it looks complicated, it's not. So I have a state x, I have of course a delta of it because the helicopter is here, I want it to be here, so I just compute the difference, and then I'm feeding it back. And we're doing some state transformation because we have some higher order time derivatives in the end there of the input matrix. And, well, if you linearize your system about the point where you want to be, you get where you want to be because you eliminate differences. So this looks complicated, but in the end you have simply a position controller that feeds your helicopter this position. Then you have the inner loop that defines velocities in these angular velocities in these three directions. And finally you just define these two velocities. So I'm going to show one last video. I'm hoping it's working. And we did that at the team I was working with. You want to do that? So that's MATLAB, but you can MATLAB is nice for it because it has toolboxes, like a navigational toolbox. But you can do that as well with Maxima. So we're hovering at at a given position, and then it's flying half of a circle. And the problem here is that this was still done using Euler angles, and what you can see really nicely is that the helicopter doesn't turn, so you're facing just one direction. We are not that far right now to have implemented quaternions, but then you should be able to, no, well, not this way, but move any direction that you want to do. So one last word concerning the usefulness of this stuff, because helicopters, like drones, are in the media right now. You can do bad stuff with everything, you can do nice stuff with everything. One approach of this thing, well, I was doing research in Canada, and you have vast fields of nothing. You have power lines supplying one little town somewhere out of nowhere in, I don't know, Saskatchewan, where you need power, and then you have a line that breaks. And what they do is they use a helicopter, so a really good pilot, he flies up there, then they have an electrician, he sits well on the brim of the helicopter, and then he repairs stuff. And that's done with a helicopter. And usually if you learn to fly, you use a football field or something to land, because you can't navigate that accurately. And well, just imagine you have a power line where you have like this error. And so you could do that with helicopters as well. Or we had a nice little podcast of someone telling a story where they measured vortex effects at those huge windmills that are standing around here, because these vortex effects, they affect the whole ground around it. They measure weather effects, like they have airplanes going up into the stratosphere and then just circling slowly down and measuring over 30 minutes weather effects and so on. So you don't have to do bad stuff like surveying people, but you can do good stuff with it as well. So thank you very much.
Oh, we have time for a few questions. If somebody wants to come to this microphone. Anyone? Give it a few seconds. Okay.
So if you have further questions, we are where the nice wooden geodesic dome is. So come over, have a drink, and we can chat. Yes?
Actually, maybe a bit stupid with respect to what you've just shown, but are you familiar with all the algorithms that are being implemented in all these UAV that we see around, these model UAV, like Parrot, like the paparazzi, all this kind of stuff that seem to be flying so easily? I'm asking this because I also had students working on all this, and they also made all the equation, and at the end of the day, it doesn't fly. So how do these guys get their UAV flying? Do they also go through all this, and do they do something additional to get it work in real life, or?
I'm sorry, I had problems understanding the question. So what's the question?
We see around us a lot of ULV lately, which are Arduino-based, paparazzi-based.
So paparazzi is,
What kind of algorithm do these guys implement in their flying algorithm?
So paparazzi is pretty much, well, kind of the same thing. So they have a wiki where you can find all the information. So for you guys that don't know about paparazzi, it's the open source project for flying airplanes as well as quadrocopters, where you can get a copter, get the software, it's open source, you can change stuff and then just fly. It's pretty nice. But they, at least what I got from their website, is that they did PI control. That's the most basic approach that you can do. And I'm looking into it now because I'm pretty interested in it, but I don't know how paparazzi is doing it. What I know is that the military, well, they're working on it longer, they have more money. That's not just one student working on it, like we did with our research. So they do pretty complicated stuff to have all those drones flying around. And the stuff that flies here, well, that's controlled manually. It's not controlled autonomously. And basically, with the drones, often you have someone sitting at a military base with a little camera and as well a joystick or something controlling it in case of buildings appearing or whatever. So, yes, but check out paparazzi. They're pretty neat.